Today, I'm going to show you how to maximize your knife sharpness to the max, and show you the principles behind the most important part of what makes a knife a knife. Geometry. So that you can not only get the most edge retention, but also the most strength and toughness for your given steel and heat treatment. In some cases, manipulating the geometry or the angle of the sharpened portion of the knife can mean a massive difference in edge retention, toughness, and strength, depending on what you're cutting. Now, first off, geometry in the knife world refers to everything that makes the wedge shape of a knife. This includes both the primary grind and the secondary grind, or the actual sharpened portion of the knife. Geometry is also blade stock thickness, so everything that involves a blade's thickness at any given point along the blade is geometry. Now in this video, we'll be focusing on the secondary bevel, the actual sharpened portion that forms the apex of the knife. Now the angles that we will be referring to later here in this video will be in degrees per side, which is the angle relative to the blade's center line. Now you'll also hear occasionally in the knife world something called the inclusive angle, which is the angle relative to the other side of the bevel. Now, the inclusive angle is rarely used when discussing apex geometry. It's almost always in degrees relative to the center line of the knife blade, or degrees per side, or DPS for short. Now there are several different ways a knife edge can dull. Now some of this is overlapping depending on how closely, literally how closely you look at the apex under magnification, but generally speaking, there's three different ways in which a knife edge can dull. The first is through abrasive wear. That's where the apex is physically worn away in very small pieces. You can think of abrasive wear as a knife's edge cutting through sandpaper. The fine sandpaper particles will essentially sand away the fine apex over time to a duller, more rounded over point. This type of edge dulling is generally controlled by the knife's steel type and heat treatment. Higher hardness and more abrasion-resistant steels will resist abrasive type dulling better. Now, this type of dulling is fixed. You can't do anything about it. You can't reheat treat the blade or change the steel type at home. However, the last two ways that a knife can dull, which is what we'll be focusing on in this video, can be changed at home through geometry. Now, the second way that a knife can dull is by apex rolling. This is where the entire point of the apex rolls over to one side or the other, or even when the apex is smashed down onto itself like Play-Doh. Now, the third way that a knife edge can dull is through apex chipping. This is where the fine point of the apex actually breaks off rather than bends or deforms. Now, these last two things, both apex rolling and apex chipping, can be summed up in one term called apex stability. Essentially, we want that microscopic apex to remain standing in order to act as a wedge and wedge things apart or cut. And because a knife is simply a wedge, the steeper the wedge, the sharper the knife. It's literally that simple. Now you can visualize this as if we have two wedges. One wedge is very acute. The other is more obtuse. If we were to wear these edges away at an equal distance from the apex and measure the width of the apex on each wedge at an equal distance from the original apex, you would see that the super acute wedge is still going to be sharper because it's thinner. However, if the secondary bevel or sharpened bevel of the knife is so thin that the apex rolls or chips due to a lack of strength or toughness, a thin apex may be destroyed very quickly depending on what you are cutting. So you need to balance the secondary bevel geometry in order to give you the thinnest wedge possible and still have the toughness and strength to withstand the stresses involved in cutting through whatever it is that you're cutting. So to give you a real life example of this, I'm going to take a Volstead Raccoon with 14C28N stainless steel and do some apex stability testing. I start off at a pretty steep 17 degrees per side secondary bevel angle and cut some cardboard and some zip ties. The knife performed very well at 17 degrees per side. Now, cardboard and zip ties are hardly hard to cut. So what would happen if the knife impacted something it wasn't supposed to? like a staple in a box, for example. Well, to simulate this in a somewhat scientific way, I did a brass rod drop test. Basically, I drop a 2x4 onto the knife, which is on top of a brass rod at a set distance to see how the apex holds up. As you can see, we sustained some major damage here. Not much of a surprise at 17 degrees. Now how about 18 degrees per side? Well, I had to change my magnification because the damage was so great. Now I ran through this same test, increasing the angle by 1 degree every time, and you can see we get to a point at around 22 to 24 degrees per side where the damage just goes away completely. We really can't even tell anything happened to the apex at 24 degrees per side. This would be a really good, tough working edge, and a more extreme 17 to 18 degrees would be a great performance cutting edge. Now another test that I like to do for apex stability is the 2x4 chip twist test. Basically, that involves digging the knife edge into a 2x4 and twisting it in the wood, causing a lot of lateral stress on the apex. This is a really good test for testing apex stability, and to show you how two different steels at different hardness levels respond to this twisting, here's VG10 at 58 HRC at 15 degrees per side after the twisting chip test. We can definitely see some major chipping and micro chipping along the apex. Now here's a CPM M4 at 63.6 HRC at the same 15 degrees per side after the same wood twist test. This apex held up much better on this test at this pretty extreme 15 degree angle. Now if we look at these same two steels after the brass rod test at 15 degrees per side, they look pretty much identical to my calibrated eyeball. Now, in my mind, this is somewhat interesting because technically this shouldn't be the case. It may be a better geometry test with the steel differences being irrelevant, but it may actually showcase a flaw in the test when comparing different steels. When looking at VG10, 14C28N, CPM M4, and a $1 knife from the dollar store, they all look too close to call except for the $1 knife from the dollar store, showing ever so slightly more deformation on the brass rod test. Perhaps this brass rod test works more like HRC testing in that the more the knife wedge pushes the brass out of the way, the greater it protects the fine apex from damage regardless of what type of steel it is. Essentially, the knife edge penetrates the brass rod the same amount under the same force at the same angles. This could limit the damage the apex sustains, although you would still think that this wouldn't be the case and you'd be able to see some differences between steels, but let's save this rabbit hole for another video. The point here is still the same. In order to maximize cutting performance, we need a very thin wedge, but only thin enough to cut what we need without sustaining damage as we're cutting. So whether you are freehand sharpening or using a fixed angle system, thin that wedge out until the apex starts to fold or chip. At that point, add a couple of degrees back to the angle until the damage stops. At that point, you've maximized your edge retention and cutting performance for the given task. And keep in mind that this can change depending on what you're cutting. Also note the difference between just 2 degrees per side is the difference between damage and no damage. This, even on a microscopic scale, is an extremely small amount of material. And I think it does highlight some of the advantages of using a fixed angle system since freehand sharpening isn't that accurate. So don't be afraid to manipulate the cutting edge. You could be leaving a lot of performance on the table.